Hey there guys, this is Future Gomi here, just starting out right before this video because this video is when we first start talking about logical theory. So, I ended up missing this in my original tutorial for how the gates work, and I ended up editing these images later for this purpose. So you're going to see on screen right now these scientific symbols for the AND gate, the NOT gate, the OR gate, and the XOR gate, and now you'll be seeing the NAND gate, the NOR gate, and the XNOR gate. Now you need to know each of these symbols, which should be pretty easy once you get the main idea down. An AND gate is a rounded bottom with a flat top. An OR gate is the same thing but with a curved top. And an XOR gate is the same thing but with an extra curve right above the curved top. And then for any negated gate, the output has a circle on it. That's really it. So let's get started with the actual video. Hey there everyone, it's Gomi and welcome back to the Logic tutorial series. Now today we are talking about binary. The specific circuits that we are going to be going over in this video are going to be the binary adder, binary subtractor, and binary to hexadecimal display conversion. Now I won't be giving you guys all of the schematics for how to make it display. I will, however, be giving you guys the circuit diagrams for how to make the binary half adder, binary full adder, binary half subtractor, and binary full subtractor, just in case you might ever want to use those. However, the first thing that we're going to do is look at our display. But first things first, you need to understand how exactly binary works. Binary is a system of ones and zeros that tells you anything that you need to know. So a lot of the time you will see people using binary to express numbers, but binary can also be used to express symbols or letters if you are using a system like ASCII. So let's go over what exactly this display will do whenever we put in our first bit of binary. It shows a 1. This is our first bit, and then we can also turn on our second bit and see 2. This is because in binary, every bit after your first bit, well, every bit after another bit will be 2 times that last bit. You can also find the value of any given bit using the equation 2 to the power of n minus 1, with n being the bit number, where it places compared to other bits. So, we know that we have this very simple circuit that tells us, okay, when we have one bit, it's 1. When we have our second bit, it is 2. But when we have both, it is 3. The way that it does this is through a very optimized method of display. And what I want to show you guys is how exactly you can use this method of display for yourself. And it's something that I have failed to use in a lot of my projects, but it's something very important that you should use if you are learning logic. And it's not just something that you use in binary. You can use it in almost any display that you'll ever be working on if it really does include things like numbers or letters, and probably a lot of other applications as well. So, let's go over exactly how this works. If we go ahead and turn on our first bit, we see where all of the levers going out from it go. We see 3 wires. I think I said levers, I meant wires. We see 3 wires going out. These wires, first of all, go into this NOT gate. We'll come back to that later. But they also come to these 2. We see it go into this OR gate, which turns this wire on. This wire goes into this wire, and that makes it display a 1. Now, why we do this is because in any case of 1 being on, we always know that this will be on as well. However, this OR gate also takes a value from 2, which means that if 1 or 2 is on, then this wire will be on, which we also know to be true. But because we are just doing this with an OR gate and not an XOR gate, that means that it also ends up on if we have 3 on. Now, that works perfectly because all of these numbers have the same display wire on in any given situation, which is this top right display unit. Now, this won't work for a lot of numbers or even in a lot of systems because once you start getting up to higher and higher numbers, you see that there starts to be a lot less combinations that you can do. However, this is still something you can use to display much more efficiently. If you're using systems like this where you use OR, XOR, NOT gates, AND gates, and any other sort of circuit that you can get your hands on that will work for this, such as this AND gate and NOT gate combo, you can figure out exactly how you're going to do stuff like this. Now, let's go over this AND and NOT gate combo, because I know you're all itching to hear about it. So the first thing that we see is because of this NOT gate, this half of the AND gate is always on except for if 1 is on. But if we go ahead and turn 2 on, then it sends an output because 1 is not on. So that means that this is only activated whenever 2 is activated. So if we go ahead and turn on both 1 and 2, we can see that it never activates. This is helpful because we actually only ever have this on when 2 is on, and it's not also on when 3 is on, so we cannot include when 1 is on. We can also see that 2, whenever it is on, turns on these 3 middle display units. This is because whenever 2 is on, you only really have 2 values that you can get to, which will be 2 or 3. And 2 and 3 both have this middle portion on, so you can leave that on as long as 2 is on. And then, because 1 automatically turns this on, and 2 and 1 both turn this on, we can see that 3 is always present whenever 2 and 1 are on, this is always present whenever 2 is on, and this is always present whenever 1 is on, with this also being present whenever 2 is on. That is just the basics of how you can use this optimization tactic. However, there'll probably be a video going more in depth on it in the future of this series. Again, we really are just starting to learn how logic works and some of the systems that we use for it, like binary. So we don't want to go too in depth and get you out of the series too quickly, because you might not really like it when we start throwing more complex things at you. So we want to get you there gradually, make sure that you learn everything that you need to first, and then you can start getting onto circuit crafting, really working with binary, working with displays, and making your own full builds. One of the builds that I have planned for this series is tic-tac-toe. So we want to get you there as quickly, but also as efficiently as possible. Now, I want to show you a circuit that is a bit harder to do the optimization for. This one is, I would say, easier than the adder, but much harder than the display converter. So what we want to show you guys right now is going to be the circuit diagram for the half and full subtractor. Those are on screen right now. Copy them down, pause the video, whatever you need to do to go ahead and get those working for you. Now, since you have those, if you want to follow along with this, you can go ahead and do so, but again, you don't really know how the optimization strategy works in full, so only do so if you're willing to go through a little bit of trial and error, which is kind of how the display method works anyways. Let's go ahead and input 1. Let's add 2. That gives us 3. So technically speaking, these 2 bits also add together, just like they would if you did a 1 and a 2 in a binary adder. However, that's a really weird way to think about it, because it ultimately is just this number. It's not really adding them together, it's just realizing these 2 are together. So, we can also display the negative numbers. We have -1, -2, well, -3, and -2. That's my bad. Anyways, we have the negatives and the positives of each of these numbers, which means that if I turn on both of these and both of these, we get -3 plus +3, which gives us 0. The same happens if we have +2 plus -2. And I'm calling it addition because ultimately, a subtractor is basically just an addition sequence. That's really all that we're doing here. We're facing the same additive thing as we would with an adder, because the circuit is only slightly different from what you would actually see in a normal adder. If I also do 1 plus -1, we get 0. But if I do 1 plus -2, we get -1, and this also goes for every single other number. Which means that we can go down to -3 and up to +3 with every number in between. This is a little bit harder to explain than just the optimization tactic or, what this circuit does, right? It's barely even a circuit. So, we're actually going to leave out all of the nitty-gritty bits and pieces of how exactly this works in this video today. When we get to circuit crafting and the more complex logic, I will show you guys exactly how and why circuits like these work. But just understand that binary is going to show you guys a lot of how optimization works and the real good uses of XOR gates, like this one right here. Ultimately, this video is just focusing on showing you how binary works, what circuits we can make in binary, and how it can work to better optimize our builds. Let's go ahead and take a look at our binary adder. This uses a half adder circuit, which is right here, a full adder, which is right here, and then all of our display optimization units. So if I go ahead and turn on 1, and then 2, and then 4, and then 6, we can see that all of those numbers display perfectly. This is because I spent multiple hours of my life working on making the display work. This is only because I have not actually really used this method ever before in my building. I'm not awfully sure if this is the most optimized that I could make this build, but I did want to go ahead and make it for the video and see if you guys would be able to do so yourself. So if you're feeling confident about your abilities to do the optimization tactic, go ahead and try this challenge. Also, I forgot, so here are the designs for the half and full adder circuits. Go ahead and use those whenever you want to. You can go ahead and test them in game right now, pause the video, do whatever you need to do, and let's get back to talking. So, we've seen in this video what we're doing for a display, a binary to hexadecimal display. We've also seen a binary subtractor with a converter to a hexadecimal display, and a binary adder with a converter to a hexadecimal display. So that's really all that we have for this video. There's not much else I really wanted to go over except for what binary is, how you can use binary, and what circuits you can make with binary. So thank you all so much for watching. If you learned something, go ahead and share it with someone else that you think might learn something from it. And if you might, go ahead and like and subscribe. Have a great day.